Good morning or good afternoon. In this video, we will be covering our electrolyte solutions, our milliequivalents, our milliosmoles, and our millimoles. The molecules of chemical compounds in solutions may remain intact, or they may dissociate into particles known as ions, which has a positive charge and a negative charge. Substances that are not that are not dissociated are called non-electrolytes because they relatively stay intact, and while those that dissociate are called electrolytes. So urea and dextrose are examples of non-electrolytes in the body, meaning when you expose them to water, they remain the same. While sodium chloride in the body fluids is an example of an electrolyte. So an electrolyte is a substance that when exposed to water dissociates into its cation and anion portion. So in the case of our table salt or our sodium chloride, it dissociates into sodium cation and our chloride cation. So they dissociate into two different species. So sodium chloride provides sodium and chloride ions which carry electrical charges. Electrolyte ions in the blood plasma include our sodium, potassium, calcium, magnesium, and the anions chloride, bicarbonate, phosphate, and our sulfate, organic acids, and protein. So why do we need to learn about our electrolytes? It's because some of our dosage forms are not expressed in milligrams or grams or in percent. They are expressed in the differently, like our milliequivalents or our milliosmoles. So electrolyte preparations are used in the treatment of disturbances of electrolyte and fluid imbalance in the body. In clinical practice, they are provided in the form of oral solutions or syrups, dry granules, or intravenous infusion. So as you can see on the right, you can see Pedialyte, and you can also see Hydrite, which is one of the most popular oral rehydration salts. So if you actually inspect the bottle or the box, it doesn't give you milligrams or grams. It only gives you milliequivalents. And the first unit we will be talking about is our milliequivalents. So the chemical unit milliequivalent is used to express the concentrations of electrolytes in solutions. Okay? So this is different from grams, in which you describe the weight of a substance. This is a unit of measure that is related to the total ionic charges in the solution and takes note of the valence of the ions, meaning it's more of a unit of chemical activity of an electrolyte. Mostly you can find this in the United States. However, here in the Philippines, we do use milliequivalents as well. However, the SI counterpart of our milliequivalents is our millimoles or our micromoles. Okay, so here is the formula for milliequivalents, but I would like to write it so you could more easily remember the formula. So for milliequivalents, the formula for milliequivalents is milligrams multiplied by our valence on top and molecular weight on the bottom. Okay, so molecular weight, you can find this as the weight of the substance or the chemical formula or the chemical weight of the substance. You can find it in our periodic table, or you can find it as in several resources. Now, in this case, you don't need to convert MW into grams. You can actually use it as no unit. You can express it as no unit. So basically, it's milligram times valence, and there's no unit on the bottom. So milliequivalence is milligrams times valence over our molecular weight. So our valence comes from the charges of the ions. Take for example, calcium plus 2, it has a charge of 2. Sodium plus 1, it has a charge of 1. Phosphorus has a charge of 3. Sulfate, let's have sulfate. It has a charge of negative 2. Potassium also has 1. And let's have magnesium, which has a charge of 2. Basically, what we're looking at is the charge of the ion. That's the valence. That's where you get the valence. For the opposite, if you want to get milligrams, you multiply it with the milliequivalent weight. This time, the valence is on the bottom, and what is on top is the molecular weight of the substance. And you would get your milligrams. If you are dealing with concentrations like in milligram per ml to milliequivalent per ml, you simply have to include milliliters in the formula. So it's in milligram per ml multiplied by molecular weight on the bottom and valence on top. And you will have your milliequivalent per liter. Okay. A good reminder or a good tip is milligrams will always cross with molecular weight, and milliequivalents will always cross with valence. So that's just a tip for you to remember the formula. Okay, so let's have a sample problem. What is the concentration in milligrams per milliliter of a solution which contains 2 milliequivalents of potassium chloride per milliliter? Now, in cases in which you are dealing with whole compounds like potassium chloride, you're only going to get the sum, or you're going to get the valence of only one ion. Since always our chemical compounds are neutral, so they would have the same valence. So take for example potassium chloride. Potassium chloride is made out of one potassium ion and one chloride ion, plus 1, negative 1. They both have a valence of 1. Therefore, the valence is 1. So what we need is milligrams per milliliter. So mg per ml equals milliequivalent per ml. Valence on the bottom. Molecular weight on top. The molecular weight is 74.5. So I'll write the plain formula first. So milligram per ml. What is our MEQ per ml? 2 per ml. 2 MEQ per milliliter. The valence is 1. The molecular weight is 74.5. And the answer is 149 milligram per ml. Next, what is the concentration in grams per milliliter of a solution which contains 4 milliequivalents of calcium chloride? So the weight of calcium chloride is 73.5. And what we need is grams per milliliter. So our formula is in milligram per ml, MEQ per ml, multiplied by valence on the bottom, molecular weight on top. So milligram per ml. Our concentration is 4 milliequivalents per ml. Our MW is 73.5. And our valence, in this case, it's calcium chloride. It's made out of one cation of calcium and 2 chloride ions. So it's positive 2, or it's 2 times negative 1, which is always also 2. So the valence is 2. And the answer is 0. I think you would have 100. Yeah, 147. 4 times 73.5 divided by 2. It is 147 milligram per ml. However, the question is not asking for milligrams, it is asking for grams. And we simply need to convert the milligrams on top. So 147 milligram per ml, multiply it with 1000 milligram is 1 gram. It's 0.147 gram per ml. That's the answer to that. Next, what is the percent weight in volume concentration of a solution containing 100 milliequivalents of ammonium chloride per liter? So ammonium chloride, the charge of ammonium is positive 1 and chloride is negative 1, so the valence is 1. Okay. So the concentration is 100 milliequivalents per liter, so 1000 ml. So we don't need to delve in too much. All we have to do is to get the concentration, but this one is in milliequivalents. So let's convert MEQ to milligrams. 1000 MEQ times valence, which is 1, multiplied by the molecular weight, which is 53.5, we would have milligrams. So that's 533.5 times 100. That's 550 milligrams per 100 ml. However, our standard unit for percent weight in volume is in gram per ml. So let's convert our milligrams into grams. We need to divide by 1000. That is 535 grams over 1000 ml. And we simply need to divide and multiply with 100%. And you have 0.535% weight in volume. Next, a magnesium level in blood plasma is determined to be 2.5 milliequivalent per liters. Express this concentration in terms of milligrams. So this one is another plain conversion. We just need to convert MEQ to liter. 2.5 MEQ per liter. Let's convert MEQ. Let's have valence on the bottom, which is positive 2. Molecular weight is 40. So 2.5 times 40 divided by 2, we will have milligrams. 2.5 times 40 divided by 2. Let me check if we have the correct molecular weight for magnesium. I think we might be mistaken. Oh, sorry, it's 24. 24. So let's this one. So 2.5 times 24 divided by 2. So the answer is 30 milligram per liter. Next, the normal potassium level in blood is 17 milligram percent. Express these concentrations in terms of milliequivalent per liter. So as we discussed last time, Milligram percent is simply 17 milligrams over 100 ml. It's simply milligram per 100 ml. And we need to convert this into milliequivalents. So first, let's convert our milligram. The bottom, we have our molecular weight, which is 39. And the valence is 1 because it's potassium. Potassium positive 1 is 1. And we will have our milliequivalents on top. And let's convert our ml into liter. 1000 ml is 1 liter. 17 divided by 100 divided by 39 times 1000. It is 4.358 milliequivalents per liter. Next unit we're going to discuss is our millimoles or our micromoles. So as noted previously, the SI units expresses electrolyte concentrations in millimoles per liter or micromoles per liter. For monovalent species, milliequivalents and millimoles are the same. A mole is a molecular weight of a substance in grams, and a millimole is just 1,000th of a mole, and a micromole is 1 millionth of a mole. Now, to get millimoles and micromoles, okay, if you want moles, you have your gram substance times the molecular weight of the substance is equivalent to 1 mole. If you want millimole, you don't have to use a different uh, molecular weight. You just have to use milligrams of substance times molecular weight on the bottom, but this time you're going to get 1 millimole. And for micromole, you have to use microgram of substance times molecular weight on the bottom multiplied is equivalent to 1 micromole. So all you need to do to get moles, millimoles, and micromoles is to divide by the molecular weight. If you have grams divided by molecular weight, you would have moles. If you have milligrams divided by molecular weight, you will have millimoles. And if you have micrograms divided by molecular weight, you would now have micromoles. Okay? So it only depends on the unit you are starting with, on what unit you will have. If you started with grams, you will have mole. If you have milligrams, you have millimoles. If you have micrograms, you have micromoles. Okay? So let's start. So how many millimoles of monobasic sodium phosphate with a molecular weight of 138 is present in 100 grams of the substance? So let's have 100 grams to millimoles. What we can do is to convert this into milligrams. So 1000 grams multiplied by 1000. So 100 grams multiplied by 1000 is 1 million. 1 million milligrams. The molecular weight is 138, and you will have 1 millimole. So 1 million divided by 138, you would have 7,246.37 millimole. If you wanted to do it this way, in which you converted it first, you got mole first. So 100 divided by 138 is 1 mole. Then 1 mole is 1000 millimoles. That is also valid. You would have the same. 100 divided by 138 times 1000. It is the same. 72. Wait. I think I had 100 times 1,000. It's only 100,000. Sorry. I had a mistake on my numbers. 37. It's 100,000 milligrams, not 1 million milligrams. Okay, so this is the answer. We started with grams, you're gonna get moles. If you started with milligrams, you're gonna get millimoles. So it's up to you what path you're going to take. Next, how many milligrams would 1 millimole of monobasic sodium phosphate weigh? So if we started with millimole, we're going to get milligrams. So 1 millimole of phosphate, phosphate is 1 millimole is to 95.98 milligrams. It's 95.98 milligrams. Yeah, it's the same. Next, convert blood plasma levels of 0.05 microgram per ml and 2 microgram per milliliter of tobramycin to mole per liter. So in this case, if we want to use microgram, we will have micromole. Then let's convert micromole into to moles. So let's start with 0.5 microgram per ml. So if we divide it with our molecular weight for 67.52, we would have micromole. And 1 times 10 to the 6 micromole is 1 mole. So we already have mole on top, and let's just convert ml on the bottom. 1000 ml is 1 liter. 0.5 times divided by 467.52 divided by 1 million times 1000. Let me check. Mole per liter. Point 0.5 divided by 7.52 divided by 1 sixth times 1000. Yeah, 1.0694 times 10 to the negative 6. And for the bottom, 2 microgram per ml times 467.52 is 1 micromole. 1 times 10 to the 6 micromole is 1 mole, and 1000 ml is 1 liter. 2 divided by 465.52, 1 is to 6 times 1000. It's a very dilute number, 1.208 times 10 to the negative 5 mole per liter, mole per liter. Next unit we have is osmolarity. So, osmotic pressure is important to biological processes that involve the diffusion of solutes or transfer of liquids through a semi-permeable membrane. The USP states that knowledge of osmolar concentrations is important, and the labels of pharmacopoeial solutions that provide intravenous replenishment of fluid, nutrients, or electrolytes, or the osmotic diuretic mannitol are required to state the osmolar concentration. Osmotic pressure is proportional to the total number of particles in the solution, and the unit we use to measure osmotic concentration is our milliosmol. Okay. Now, milliosmol is equal to millimole times species. Okay. Species is the number of particles that a single compound would give off. So if your compound is a non-electrolyte, like for example dextrose, 1 millimole is 1 milliosmol. Because it's a non-electrolyte, it does not dissociate, therefore it only has one species. Okay, so 1 millimole times species is equal to 1, that is 1 milliosmol. Now, if it's a non-electrolyte, it's the same as millimole. However, if it is an electrolyte, there is something you need to do to calculate the species. So you can assume complete dissociation. Each chemical substance that dissociates will give off daughter species. So take for example sodium chloride. It If it dissociates, it will dissociate into sodium and chloride. So this is the first species, this is the second species. So meaning the number of species for sodium chloride is 2. If you have calcium chloride, it will dissociate into 1 calcium and 2 chloride. So how many species? 1 plus 2, you have 3. So the species number for calcium chloride is 3. Okay, so you need to think, or you need to consider the ions or the salts that dissolve in water would give off different number of species. So the formula for milliosmolarity is basically millimoles times species. Species is the number of ions dissociated. So take for example this one, a solution of 156 milligrams of potassium ions per 100 ml. How many milliosmoles are represented in a liter of solution? Okay. So potassium is 39. That's the molecular weight. So 156 per 100 ml. Let's ration proportion it to get 1000 ml. How many milligrams do we have? 1000 times 156 divided by 100. So it's 1560 milligrams in a liter of solution. Now, this is the concentration we have, but this is in milligrams. Let's convert milligrams 5 into millimoles. 1560 or 1000 ml. Let's convert it to millimoles. Let's divide by molecular weight. We would get millimoles. And let's also multiply by our species number. So since it's a simple potassium ion, the species number is 1. So it's 1560 divided by 39. So it's 40 milliosmol per liter solution. Next, the solution contains 10 milligram percent of calcium ions. How many milliosmoles are represented in 1 liter of the solution? So again, 10 milligram percent is 10 milligram over 100 ml. You want it to how many liters? So let's ratio and proportion it again to 1000 ml. It's 100 milligrams per 1000 ml or per liter. Let's get calcium. What's the molecular weight of calcium? Molecular weight of calcium is 40. So let's divide by molecular weight. You will get millimole. And once you get millimole, you can multiply with the species. Please take note that the species does not relate with valence. Okay. So since it's a plain calcium ion, it's only one. So how many milliosmoles per liter? That is 100 divided by 40. 2.5 milliosmol per liter. Next, how many milliosmoles are represented in a liter of sodium chloride solution? 0.9 sodium chloride solution. So 0.9% sodium chloride solution is 0.9 gram per 100 ml. If we wanted to convert it into milligrams, zero point 0.9 times 1000, that's 900 milligrams per 100 ml. And since we need to ratio and proportion it to 1 liter, it's 900. It's 9,000 milligrams per 1 liter. Now, since it's asking for milliosmoles, let's convert our milligrams into millimoles first. The molecular weight of sodium chloride, I think it's, if I'm not mistaken, it's 58. Yes, it's 58. 58, and you will get millimole. Let's multiply it with the species. Now, since this is not a plain ion, but a compound in sodium chloride, so it's sodium chloride, it will dissociate into sodium and chloride ion. The species number is 2. So 9,000 divided by 58 times 2. It's 310.34 milliosmol per liter solution. Finally, a solution that contains 5% of anhydrous dextrose in water for injection. How many milliosmoles per liter are represented by this concentration? Okay, so 5%, let's have 1 liter, 1000 ml, multiplied by 5%. So 5% is 5 gram per 100 ml. Let's see how many grams of dextrose is there. There's 10 grams of dextrose. So that's 10,000 milligrams. And let's convert it into, let's convert this into millimoles. If I think dextrose is 180. Dextrose is 180. A millimole. The species number is 1 because dextrose is a non-electrolyte. So 10,000 divided by 180 is 55.555 milliosmol per liter. 1000 times 5 divided by 100. Ah, I miscomputed. Not actually 10 grams. I had an idea that it would be the same as zero point 0.9. So it's actually 1000 divided times 5 divided by 100 is 50 grams dextrose. So 50 grams is equal to 50,000 milligrams. 1000 times 5 divided by 100. 50,000 divided by 180 is 277.78 milliosmol per liter. So I think this is correct because it matches 0. It's close to zero point 0.9 sodium chloride. Okay. So that is how you get our milliosmol. So to summarize, we talked about our milliequivalence, which uses valence. We talked about our millimoles and micromoles, which you need the molecular weight. And you finally we have our osmolarity, in which you need to consider the number of species. That would be all. Thank you, and I hope you learned something.